Welcome to the second part of Maxima and Minima. Next Monday we have fall break. Looks like a few of your colleagues already know that and maybe are traveling. Anyone else traveling over the weekend to get out? All right, a couple of you. I wish I could, but can't go very far for just a couple of days. But have a good time, travel safe, enjoy it. What we're going to see today is going to be applications of what we learned on Monday. So we're going to be applying those skills. However, so there's nothing new as far as calculus that we're doing, but we are solving word problems that will involve geometry, some other, some words that we've got to build the equations for, and sometimes that's one of the more challenging things to teach and to learn, but it's one of the more important things as well, because the world doesn't give us all the equations we need. They give us a lot of words, and we have to figure out the situation. Okay, so that's what we're doing today. We're going to look at a lot of examples. I went through the homework and I chose an example for each type, so we'll set it up at least, and then every question that is in the homework, you should sort of have a template of at least how to get it set up and how to work through it. Again, the calculus part is not going to be all that difficult. Actually, the nice thing about real world problems, especially with geometry, it's areas length times width. There's only two things that are multiplied. So a lot of the formulas or functions we'll be dealing with are more simplistic than what we had in yesterday's or Monday's homework, but again, it's going to be setting things up that might be the bigger challenge. Don't come on Monday, we'll be closed down. Then we've got just really two more sections, a review, and then we're into our next test. And we keep moving on, and again, it's an opportunity. Look at it as an opportunity to get yourself well prepared, to do well on that, and as you do well, it's going to keep moving you forward. Remember, everyone still has an opportunity for an A in the class, an A+ if you want. But just keep working forward. If you scored well on test one, you can relax a little bit, but keep learning the stuff. If you didn't do so well, just keep moving forward and keep doing better and improving, and we'll get you there. All right, let's see. Let's get into this one. Actually, I'm in the wrong place. Want to go back a little bit. So from Monday, we found that a maximum or a minimum could occur at three different places. Okay, it could be at the endpoints. So when we set up, with what we're going with our problem solving, we want to remember to look at the endpoints of our situation. It could happen internally at what are stationary points. And does anyone remember what is special about stationary points? Or how do we find stationary points, or why are they called stationary points? Because they don't move, and they don't move because their derivative is 0. Good. So the derivative is 0, and that's what happens at a maximum or a minimum. And then there's only one other place which we probably won't see because it doesn't occur much in the natural world. Singular points where the derivative is undefined. So it's possible, but most of the stuff we're going to deal with are, like I said, real world examples that the functions don't have any place that they're not defined, the derivative's not defined at. So we'll primarily be using endpoints and places where the first derivative is 0. Okay, applications. So here is what we're doing. This is sort of what I've been talking. Sometimes we want to maximize things like profit. We're running a company to maximize profit. Or maybe we have our mission statement. We want to maximize the number of people we serve. Something. We want to maximize something, though, with whatever our endeavors are. So that's going to be one thing we're doing. Oftentimes we also want to minimize things. We want to minimize problems. We want to minimize costs, those kind of things. Maybe we want to minimize the number of hours we're in the office because we'd rather be out doing something, right? So there's all these different things that we want to do, and if we can somehow get a mathematical equation that models that process, that's what we're going to do, okay? So we're going to, in today's examples, we'll be building some fences. We'll have a few profit and loss type things that are given to us, but we'll be doing that. There's two functions that we're going to, well, actually, the equation we come up with is called our objective function. So that's going to be, like if it's a profit, we're trying to maximize profit, that's our objective function is profit. And we're looking to maximize that. Everything we do is always subject to some kind of constraints. We only have so many employees. We only have so many hours we can put into that. We only have so much money we can put into our endeavor, something like that. Those are constraints. Okay? Very few of us can just have unlimited resources. So there's a limit to what the resources we have. So we're going to use those, and oftentimes those will be our endpoints. Okay, so one of the constraints a lot of times is certain things can't be negative, like cost is either 0 or greater. Rarely do you get a negative cost, right? So that's sort of one implied constraint. Also, if you're building a fence, you can have a very short fence, but you can't have a negative fence. So there's some things like that. But then there's also extremes to the other side. We only have so much resources, so that will oftentimes give us the other endpoint. So endpoints are oftentimes delineated by the constraints. So we're going to pick those out of the story problem that we have. Okay, so we want to build an objective function, and then we want to look for the constraints. And we put those together. We'll maximize the objective function using the tools we've already learned on Monday. Okay, so the first one, we're going to walk through this example. I'm going to we'll talk through it, and then we'll work through it, and then there's about 7 slides that the textbook has done where they solved it, and I left those in here. We'll kind of just scan through them, and then I'm going to look at a few examples from the homework, and we're done. Okay, so the techniques are nothing new today. It's mostly about setting up that objective function. Once you have that, I think you'll say it's pretty straightforward. But we'll steer you through those things. So we have a clothing company. We manufacture expensive hockey jerseys, not just cheap ones. You know, we're going for top of the line stuff, and we sell them to college bookstores, right? It runs up to 500. So we'll circle that number. What do you think that 500 is? It's an endpoint. Good. It's a constraint. We can't make 4 to 500 for any bookstore for whatever reason. I don't know. Oftentimes we don't know. Anyway, we've got the cost function. They give us this, and again, maybe marketing picked that up or whatever. We're given this part. So then now we're starting to think of what the question is. How many jerseys should gymnasts, the company, produce per run to minimize average cost? So that's when you see that word, we're either maximizing or minimizing something. We're going to minimize average cost. So does that mean we just use this function here? Is that the average cost function? No, it's the total cost function. So so this is the first part. We're going to, and we'll set up the average cost function. Then we also want to know what the average cost is, and then we want to compare that to the marginal cost. Remember, we talked about sometimes we look at marginal cost. And what's the difference between average cost and marginal cost?
Marginal is like how much the next one costs.
Good. It's just the next one. So if you look at your tests, that's, as I'm assessing those, you had to make some kind of comment because it was after 200. So it's the cost of the 201st one. It's the cost of the next one. You had to say that. Some of you said it's the average cost or it's the cost of, but marginal is just the cost of just the next one. It's not continue. It's not even the second next one. It's just the next one, okay? Average cost is, if you produce 100 of them, you would divide by 100, right? And that would give you the average cost.
What did our 500 represent?
That's going to be a constraint. So it's actually going to be an endpoint. We cannot produce more than 500 for whatever reason. We don't know why, but that's what it's telling us. So that's going to be a constraint. Okay. So those are the important features. We come over here as our problem solving. Up to 500, that's a constraint. Okay, so that's going to be an endpoint. Where's the other endpoint? Can we produce less than 0? Good. Yeah, we can't produce negative jerseys, so this will indicate to us that we have a interval from 0 to 500. So those are our two endpoints. We could check those out. Let's see. We have our cost function, but we know we're trying to minimize average cost, so we need the average cost function. So I don't think we've dealt with it directly yet, but the average cost function is not the marginal, it's not the derivative. They indicate it with a bar over the top. If you've ever done any statistics, a lot of times they'll do that for the mean or the average. And what it is simply the cost function itself, the total cost function, divided by however many we end up producing. So it's Cx over x. It's the function over x. So we're going to rewrite that. And because you look at that, oh no, are we going to need the quotient rule? Actually, we don't, because the function we're going to maximize is the average cost function. And that's going to be 2,000 over x. I'm going to divide each of these by x. Let's just put the whole thing by x, which since when you add, you can separate them like this. Okay, 10x divided by x is going to be plus 10. 0.2 x squared divided by x is going to be 0.2x. And actually this 2,000 over x, let me rewrite that as 2,000 x to the minus 1, right? Because that's going to be easier to take the derivative when I need to do that. So just 2,000 x to the minus 1. That is our average cost function. And there's one very similar to this in the homework, so you'll I'm not doing, this is one that the textbook provided, and we'll get there. So we've got the function. This is our objective function. We've got the constraints from 0 to 500. Those are really the only constraints we have. And we want to minimize the average cost. So what should we do? Well, we could look at the endpoints, but if we plug in 0 to this one, 2,000 x to the minus 1, remember that is, if you plug in 0 here, what's going to happen? 2,000 divided by 0? It's going to be undefined, right? So that endpoint is kind of like, we can't really do that, but because if we produce one jersey, it's going to cost something. So that endpoint it's kind of a dead end. And who wants infinite costs anyway, right? So we could try 500. We could plug in 500 here. So the average cost at 500 is 2,500 to the minus 1 power plus 10 plus 0.2 times 500. And let me just use my handheld calculator so I don't have to go back and forth. Yes, question? Okay, no worries. Just don't want to miss a question. Okay, so we'll just plug this into a calculator. It's 2,000 times 500 raised to the negative 1 power plus 10 plus 0.2 times 500. So I get that is equal to $114. And remember, this is, think about this, this is average cost, so this is $114 per jersey. So it's the average cost. If we produce 500. I think, well, you know, the more you produce, it should be better, right? But is there a more minimum cost? Again, we could just graph it, and we will, but we'll also take the derivative and set it equal to 0, and that will give us maybe if there's another one in between there. So we want the average cost function, but now we want its derivative. A lot of symbols in that, which is the marginal average cost function. No, we won't even use that word. So it's the derivative of the average cost function. This is not the marginal. Marginal is we would take the cost and take its derivative. So this is the derivative of the average cost function, because that's what we're trying to minimize. Let's see, here it is. So the -1 comes down. So we're referring back here. This is the one we're taking the derivative of. -1 comes down. That's going to be -2,000 x to the -2 plus 10. Wait. Derivative of 10 is 0, right? I almost broke my own rule, right? That's 0. Okay, derivative of 10 is 0, and derivative of 0.2x, 0.2. Okay. Yeah, I was messing up on the easy stuff. That's the thing when you get into problem solving. Sometimes you forget the simple stuff. We want to set that equal to 0. So we could, let's see, let's subtract 0.2. So we get -2,000 x to the -2 equals, actually I think it might be easier to visualize what's going on if I write this as -2,000 over x squared, right? So I'm moving this down and writing it with a positive exponent. I'm going to subtract the 0.2. So now that's over here. Let's multiply both sides by x squared. So this cancels with this. So then I get -2,000 equals -0.2 x squared. Now what should I do? Divide by -0.2. So this becomes a positive 2,000 divided by 0.2. Um, 10,000. Is x squared. Take the square root of both sides. So what's the square root of 10,000? Good. I was hoping it was less than 500. Yeah. So what we did is, okay, let's come here. So we get that x equals 100. Now, we don't know if that's a minimum or a maximum, but we would assume it's probably a minimum, because that's what we're trying to do. But how would we figure it out? We'll plug it back into, not the derivative function, we'll go to we'll go to this one, the average cost function. Notice how we're each time using the average cost function. We're going to plug in 100 and see what we get, and then we can compare it to 114. My guess is it's going to be less, and that would show that would be a minimum. Then we're going to graph it. We're going to graph the average cost function, and we'll visually see it as well to confirm it, okay? So let's plug in, let's find C bar of 100, which is going to be 2,000, actually 2,000 divided by 100, right? Because that's down in the denominator, plus 10 plus 0.2 times 100. See, I can almost do this without the calculator. So this is going to be 20 plus 10, 2 times 100, that's 1, 2. This is also going to be 20. Move the decimal over 2 places at 20, 40, 50. Looks like it's going to cost, we make 100 jerseys, it only costs $100. Oh, no, no, $50. Okay. Just that number is 50. And again, we compare it to what the other endpoint we have. That's the only other thing. It's less than that. It must be a minimum because we know it's either a maximum or a minimum because it's a place where the derivative's zero. We know it's a stationary point from this work in the middle, taking the derivative of the average cost function, 100 is going to cost us 50 per jersey. So we'll actually make more profit than if we made 500, you know, so you always think that bulk, for some reason, I don't know, maybe it's expensive material and it costs us more. We don't know why, but we do know what. Okay, we do know we should produce 100. We'll minimize the cost. So whatever price we're selling, that should also help profits, right? I mean, the cheaper we can make them, we'll get the price we can get. So better than costing us 114. Questions? Does that make sense? Okay, so it's all about setting it up. It's all about knowing that the cost function is not what we wanted to work with. We wanted to work with the average cost function, which is just the cost function divided by x. And we'll see, just like the revenue function, oftentimes they give us what we're selling it for. Revenue function is what we're selling it for times x, however many we sell, right? So some of these kind of things. So we can say we can minimize it at this level. Let me go back to here. What is the resulting average cost? $50. Okay, so we can answer that one. How many jerseys should they produce? 100. So we answered that question. We answered this one without even trying it. You know, we plugged it back in just because we had to test whether it was a minimum or maximum. The one last thing is, how does the average cost, which is $50, compare with the marginal cost at the optimal production level? So what would be the marginal cost at 100? And then remember, we're going to take the derivative of not the average cost function, but the cost function itself. We're going to plug in 100, and that's giving us the cost to produce one more. It's not an average cost, it's the cost to produce one more. And since 500, it's 114 per jersey, what do you think is going to happen for that one more cost? Do you think it'll be more than 50 or less than 50? I'm thinking it'll be more than 50. I could be wrong, but I think it will be more than 50 because that's what it's sort of telling us. It's going to cost us more to produce more than 100. So let's see. I think I'll do this right here. So I'm going to take the derivative of the cost function itself. Derivative of 2,000 is 0. Derivative of 10x is 10. And the derivative of 0.2x squared is going to be 0.4x. And, oh my goodness, if we plug in 100 for x into the marginal, wait a minute, yeah, we plug it into the marginal because we want to see what that marginal cost is. We get 10 plus 0.4 times 100, which is 40. 40 plus 10, we get 50. Kind of makes sense that we're at the minimum cost right now and we produce one more. It didn't really cost us much more, but it wasn't less. It still costs us about 50 for one more.
Wait, did you use more than one or did you use 100?
I use 100, but it's giving us the cost of the 101st. So I guess if I do 100, why not do one extra jersey? which is weird. Does that mean 101 is the best one? It just means that, and again, remember this derivative is an estimate. The cost may be like $50.01. It might actually be a little bit more. It's just an estimate. But let's, again, since this is really the only example that was in here, let's just use, well, actually I could use this graphing calculator. Let's put it in. So let's put in the average cost function, which I could do it this way. I'm going to put the original 2000 plus 10x plus what was it, 0.2 x squared, and then I'm going to divide this all by x. So that is the average cost function. We want, let's see, our window, our constraints, we know that x could go from 0 to 500, so let's do that. Just from what we've done, we know that at 500, the average cost is 114, so let's make the y max maybe 150. -5, I think that'll give a good view, and then we're going to graph this, and that's what the graph looks like. If we come down here for the minimum, so let's go second calc. Let's go to value. I'm going to enter 100. So it goes to when x is 100, and it tells us the value is 50. And visually, I can see, yeah, that looks like probably a minimum. Yes.
So what, like we found like the average cost and the marginal cost, are they always going to be equal for the minimum?
Not necessarily. It depends on how how the costs are changing. They should be pretty close though, because the marginal cost is, if we're at the place of the minimum average cost, yeah, it should be, because again, we're going to have a horizontal tangent line, and remember the marginal is going to be using that tangent line at 100, which is horizontal. It's not changing, so it actually should, I just convinced myself, I think you're right, it will always be the same because we're at a minimum cost. We're following that tangent line. The actual cost is probably just a few cents more because, again, remember, the marginal is on the tangent line, which is a good approximation, but as we can see, the average costs start going up, so probably by a couple pennies of the actual. Good question. Any other questions? Do we see it now? We see a visual. We see, and again, this is not the cost function. Cost function is a quadratic, but this is a marginal cost. No, it's not marginal. It's an average cost. And we see that the more we produce, the average cost goes up. Yes. That's to make it the average cost. Without that, then it's the total cost function. And it's just telling us if we produce 100, that's the total cost for producing 100. With this, we're dividing by 100 each time, and so it gives us the average cost per jersey. Does that make sense? So, and again, when in business, you want to know the cost per jersey because then you want to know what to sell it at, right? That's what the price in the store is going to be. You can't, okay, this is the 150 jersey, we got to charge more for this than the first jersey or something, you know. We want to charge all our customers the same amount, so we look for the average cost. Okay, so running in batches of 100. Again, it's somewhat of a contrived thing, but you know that's what we do is we get operations gives us what the cost per jersey or what the costs are. We put those in. We can do these kind of calculations. All right. So if we're pretty good, let's go ahead and look at a couple. We're just really going to focus on setting them up. We won't solve all these ones, but I've got about 5 different examples. I'd like to at least get them set up. If you have additional questions, please do ask, because I want you to, again, these are coming directly from the homework you'll see. I want you to at least be able to say, okay, I understand how to set it up, and then you just basically go through this process. You'll plug in the endpoints and go from there. Oops, where's all my... I destroyed all my stuff. So then, actually, there's about 5 or 6 slides here. So this, if you want to take a look at it, this is the textbook going through and solving it, doing what we just did. Kind of, explaining things. And they got the same answer at 100. Actually, they got plus or minus 100, but negative 100 doesn't make sense. So it goes in a little bit more detail. And then they even show the graph. Okay, so it's a good process. So always, again, you don't have to produce a graph, but it's always a good thing to look at the graph. It'll verify your solution and everything that's going on. Okay, so now let's get into some homework examples to at least get them set up. So there's a few questions involving some geometry. How many of you took geometry last semester? Nobody. Probably hasn't been since high school, or maybe a few years. In fact, we don't do a good job in the U.S. curriculum of teaching geometry. I was fortunate enough to have one of my mentors. He always would make me tie algebra and geometry concepts together. He was good at it. I wasn't, but he got me better. Okay, so we've got a rectangle with a perimeter of 76. We want it to have the largest area. Okay, so when we go to the largest area, that's what we're going to maximize. So we need a formula for the area. Again, that's going to be our objective. What is your objective? To maximize area. So area is something we need. Well, if I've got a rectangle, the features I know, there's a length and there's a width, there's a base and there's a height, however you want to do it. There's 2 dimensions that if I multiply them together, I will get that the area is the length times the width. Okay, so that's going to be our objective function. Notice it has 2 variables, and we've only been doing calculus really with 1 variable. Actually, 3 variables if you want to count the a. But so what we do is we also have a constraint over here. We know that this rectangle is limited to having a perimeter of 76. So maybe this is like fencing. We have 76 feet of fence to make this rectangle, whatever it is, or string to, So we can make the rectangle of whatever dimensions we want, but this is a constraint. We only have 76 units of stuff to work with. So then we also need to know what's the formula for perimeter in terms of the length and the width. Oh no, see, no, it's okay. We forget about these things, right? Perimeter is the distance around. So if you're some little ant or little person, and we're going to walk around this thing, notice we have 2 lengths and 2 widths. So perimeter is 2 lengths plus 2 widths. Okay. We know that's 76. And so we're able to say that our perimeter is 76 exactly. So we have 2 times the length. I'll use that kind of a L plus 2 times the width. What we're going to do is we use that formula, that perimeter formula, to solve for one of the variables, and then we're going to substitute in our area formula so we only have 1 variable. We have either the length or the width. Doesn't matter which one. You could do it either way. Okay. So the perimeter formula, do you want to solve for the length or the width? Length. Sounds good. So we want to solve this formula for the length. And again, I'll do a little bit, but we won't go all the way because I just want you to, oops, this is not x, it's w, minus 2w. So we have 76 minus 2w equals 2L. We'll divide by 2. Divide this whole thing by 2. And again, you could do that individually as well. And let's do that. 76 divided by 2 is 34. I think it's 38. Yeah, I think so. Okay, good. So this is 38 minus W equals L. And then what we're going to do with that L is we're going to replace this L in the area formula with 38 minus W. Okay, so we'll get that our area is 38 minus W times W. And that's what we want to maximize. What you see is you will get a quadratic. Again, we can go ahead and do that. 38W minus W squared. You could graph it. It's going to be an upside down parabola, so there will be a maximum. Our constraints, we can't have zero, right? You can't have zero area. You can't have less than zero area at least. And then there's some other end, but if you think of an upside down parabola, the maximum is going to occur at the vertex, right? So we're not too worried about endpoints on this one, but graph it and you'll see the only thing that's going to be of interest is the stationary point. So take the derivative, set it equal to 0, you'll get a value, and go from there. Once you've solved for what W is, you come back over, you plug it in here, 38 minus W, that will give you what the length is. Make sense? And don't be surprised if you get a square, because usually squares maximize area as far as rectangles. In fact, that's part of what these questions, you always end up with a square, usually, unless something weird's going on, but I'll bet you get some kind of a square. Is that good to get you started? There's a couple others in there with fencing. I'm going to set up a triangle with fencing problem, because they'll say fence on one side costs $2, the other fencing costs $8 or something, so different cost of fencing, and you want to actually minimize the cost. So we'll take a look at what that might look like. But this at least gets you anything with a rectangle. We're using perimeter and area functions one way or the other, solving one for one of the variables and substituting in. So you'll have this kind of thing going on. Again, the calculus part's not going to be too hard. Take the derivative of this. Not bad. It's all the algebra and the geometry.
So when you take the derivative of that, that's what gives you the answer.
You take the derivative and set it equal to 0, that's going to give you where the maximum occurs, right? It's going to give you the x value, or the x value. You'll have to plug it back into here to get what the area is, and then
After you take the derivative.
yeah, take the derivative. So take this derivative, set it equal to 0, that will give you the width. And you might get two answers. I think we'll just get one, but I think you'll get one answer where the derivative, because there's only one vertex on a parabola. Graph it, make sure. And then you're going to plug it back in here because the question wants us to give the length and the width. So then you can find what the length is. And again, I think you might get a square. Yeah, okay, good. And it says enter the smaller value first. Since they're both the same, a square is going to have both the same length and width. But okay, we'll keep moving. Oops. This is a little bit of a mess, so let me realize. Let's get rid of that. I'll get rid of this stuff. Again, it's recorded, so we'll post all of that. But this is a problem right out of the homework. And the red parts are what will be different. So this constraint of 258 was what I came up with. When you work it, it might be different. But again, we just sort of want to set this up. So Postal Service will accept packages only if the length plus the girth is no more than 258 inches. Assuming that the front face of the package is a square, what is the largest volume of the package? So if this is a square, what do we want to do? Well, we know that whatever this is going to be the same. So our dimensions are x times x, and then we just got to figure out something for the length. And what we're trying to maximize, what we're trying to make the largest, is the volume. And again, just have to remember that volume is length times width times height. Our width and our height are both x. So we're going to get our volume is equal to the length times x squared. And how do we get that length? Well, we know, or we're given, this constraint up here of 258, that the length plus the girth is no more than 258. So what is the length plus the girth? Well, we have the length. The girth is going to be all this, is the perimeter of this square, right? We've got 4 sides. Each side is x. So that's going to be 4x. And we know that when we add those two together, it can't be more than 258. But let's use up all the 258 to get the most volume we can. And again, what we're going to do is we're going to solve for either x or L. I would assume solving for L would probably be the easiest. It'll go in here, right? Minus 4x, minus 4x. So we get length equals 258 minus 4x. We do a substitution into here so that we get the volume is 258 minus 4x, x squared. That's what we want to maximize. You could maybe multiply through. You're going to get a cubic function, right? It's going to be x cubed, 258x. Again, yours will maybe have a different number than 258, but this is the setup. We want to maximize this. The constraint has been considered by limiting the girth. The post office has given us that. So this has it all. So basically take the derivative. Now with a cubic, you could have 2. So you know how a cubic goes? It goes up and it comes down, or it's down and up. Yes? 4x is because I figured out girth. Girth, they didn't tell us directly, but they're showing that the girth is the measurement around, it's the perimeter of this face. And so since I called one side x, there's going to be 4x. It would be, because it's a square. Now, if it's not a square, then that makes it really a little bit more complicated. We have to know something about this. So that's this perimeter. That's what the girth. So 4x is the girth. The length is the length. And so if I take the length plus the girth, it's got to be 258 or less. But we're going to maximize it out with 258. Does that help? Okay. So you see this idea of perimeter again being factored in there. And the fact that they made it a square is what's going to make it easier. And as you saw in the other one, squares maximize area. So they also, by having it a square, that's probably going to give us the maximum volume anyway. Made the mathematics a little easier to work with, and it ends up being something that's going to maximize our volume. So far, so good? Okay, we got maybe 2 more to go. Okay, now there's one with a triangle. We're building fences, and again, this one we can use a triangle because it's you can read through here, but there's a nice little river flowing, and we want to block. I guess we want to block access to our beautiful flowers or whatever it is. Our garden. We don't want people. We don't want the deer eating our beautiful garden, our hard work, whatever. We need a fence, and so they do give us a hint. We want to enclose as much as we can because we want as much garden enclosed as we can. Area is going to be x times y over 2, base times height, right? Area of a triangle, 1/2 base times height. And so you call one side x, the other side y. That's the length. But here's where it gets a little complicated is the left border, so what I'm calling y, the fence is going to cost $10 per foot. So maybe that's where that's close to the road or something, it's more expensive fencing. And then the fence on the lower border, maybe it's just in the field, is cheaper. It's only going to cost us $2 per foot. And we want to spend $520. So that's we got a budget. Okay. So how do we get cost? Well, $10 per foot times how many feet we use on this border on Y, plus $2 per foot times X. X is how many feet is on the border. That has to equal 520. Again, this is a constraint. This is our budget. This is all the money we have, and we've chosen the types of fences. So that's, again, and you'll see probably X is going to be bigger than Y because it's cheaper, you know. But that's that's our constraint. And then the objective function, the thing we want to maximize, is that we want to maximize the area, and that's simply x times y over 2. Base times height divided by 2, 1/2 base times height. Okay. So again, all we need to do is solve this constraint function, this for either x or y, substitute that in, so we only have one variable. You'll see this again. We can't do math if there's two variables, because there's two things changing at the same time. We can do it, but we need some tools that we're not just going to spend the time to get. That's multivariable calculus, which even in engineering they'll do, but that's like Calc 3 or 4. It's down the road. So we're not doing any multivariable stuff, so we'll solve for either x and y, and it doesn't matter which. Plug it in here. You'll be able to then use the derivative, and notice the way it works, it'll be a quadratic function again. Quadratics always have a vertex, which is either a minimum or a maximum, and in this case we're trying to maximize, so you'll see it'll all come together. But is that good for the setup? Okay. There's another one like this, but it uses a rectangular garden, so you'll be basically putting the two together from the first one that we did on rectangles and cost. And again, just remember the constraint function is, you know, whatever your perimeter. So, and the reason we don't have a third side here is because we've got a river. We don't have to put a fence by the river. That's going to be our sort of third fence for free. But because it's a triangle, if we needed a fence on that side, we'd actually have a third thing here, right? Which would be the hypotenuse. And again, it would make it more complicated. We could use the Pythagorean theorem and all that stuff, but this makes it easier. We okay with that? I think we got one more example. Yeah, so actually I have two more. This related to the same question. This is dealing with the business concept of costs and profit and loss and revenue and those things. So I wanted to kind of walk through this one in getting it set up. Okay, so we're producing a film. Let's see, what are we doing? The price of the video release. They don't make videos anymore, do they? So this is an old question. Or maybe do they still make videos? I don't know. Do they still have DVDs, huh? You just stream it, right? Yeah, I don't know. Anyway, old question. The marketing people estimate that the price of P dollars, it can sell a total. So this is kind of a demand. If we change our price, right? If we make our price higher, we'll sell fewer. So this is basically our demand. What price will bring in the greatest revenue? Okay, so this is how do we set this up? This is our demand function. This is how many we can sell. So how do we get revenue? Revenue is, let's think of the newspaper. I sell my newspaper for 75 cents and I sell 500 copies. How do I get my revenue? 75 cents times 500. So the amount I sell times the price. What we've got is Q is the amount we will sell. We need to multiply that by the price, and that will give us the revenue. Revenue is demand or amount sold times price. So what we'll write it as is 2,800 minus 20,000. Yeah, 20,000 P. This is how many we're going to sell times P again. Okay, so you see this and it's kind of, where's that other P coming from? That's the price. The first one, the other P in there is what's determined by how many you can sell. And notice we'll get a quadratic, right? So this is revenue. And the question is, we want to maximize revenue. So this is our objective function. That's our objective. This is sort of a constraint, but it gives us this. Again, we can just distribute the P, which will make it easier to take the derivative. And where that's equal to 0, that gives us a minimum or maximum. Again, graph it, you'll see it's a quadratic that's got a negative coefficient, so it's going to be an upside down parabola. It's going to have a maximum. Find where that is. Okay? And that's all it's asking for, is once we solve for P, it only wanted the price. The next question, though, very similar question, but they're doing, this is the bride of the son of, so they're making another movie. A different function, similar but different. But then they also give us a cost, because we need to have the cost to figure out profit. And that's what they want. What's the greatest profit? So again, remember, this is all in the setup. What is profit? Profit is revenue minus the cost. Okay. Now we could kind of see we're going to have to change it because this is a slightly different function, but revenue is going to be this function they give us. It's going to be Q times P, right? So that we picked up from the first question. And I'm going to go ahead and distribute it. So it's 200,000 P minus 20,000 P squared. That's revenue. We need to subtract the cost, but how do we get the cost function? They gave it to us here, $4 per copy. $4 per copy. Well, P is price. Where do we have the number of copies we're making? Q is how many we made. Yeah, I was almost going to go, it's just 4P. That would be simple, but it's not 4 times the price, it's 4 times how many we made. And how many we made is this function here, based on the price. Okay, so you're going to want to take the $4 times Q, which instead of writing Q, I'm going to write out this expression, 200,000 minus 20,000 P. So it's a little bit more involved, but you can see where you can, expand this out. It's still going to be quadratic. You're going to get some like terms in here. You're going to get a constant term, but when you take its derivative, that goes away, right? So that's kind of a nice thing. And this is our profit function. It's got the constraints built into it, because Q is really the constraint, as this is how much we could sell at a given price. And I guess we're thinking you wouldn't sell them for 0. So the price is going to be positive. And there's probably some limit to what you could charge, but we don't really need to get to that limit. I mean, we could say, yeah, if you charge too much, nobody's going to buy anything. That would be the other end point, but it's probably not worth even looking at. Simplify this a bit, take its derivative. What do we do with the derivative? set it equal to 0. That's going to give us the stationary point. We take that value, so we take the derivative. Let me just kind of write that out. So this is the profit function. We're going to take the derivative, set it equal to 0. Oh, this is hard. We got these p's, which are actually price. This is the profit function. We use, let's see, p of x. So profit function, we set it equal to 0. That's going to give us some value for p, right? Actually, we don't have to put it back in and see what the profit is. But we should, just to see what that is a maximum profit if you look on the graph. But the question is only asking what price should we charge. So once you have it, once you take the derivative, set it equal to 0, you'll solve for p. That's going to be some number. That's the price you should charge, and that's what they want here. Okay, so once you solve this, you'll get p equals something, and then that's your answer right up there.
Wait, so you have to first you have to simplify this.
Yeah.
Simplify that, and then take the derivative of what you get from that.
Yep. Let's take the derivative, set it equal to 0, and that's the answer. Does that make sense? Thinking through these? Okay. But I want you to see, look at these, because you can count on it again that you're going to see a problem with profit, revenue, and cost. And again, looking at some of the problems I saw was just getting this basic setup of profit is revenue minus cost. Okay, and revenue is price times quantity. All these things that you need to know. So this is just sort of a review. Identify the unknowns like we did. Figure out what the objective function, we did that. Identify whatever constraints there are. State the optimization problem and then take its derivative. Eliminate any extra variables. So we did that by solving and getting it down to one variable. Find the absolute maximum based on those theories, which was basically take its derivative, set it equal to 0. That gives us that location. Okay. Remember to also check the endpoints. Those might be sometimes the maximum. What you all doing Monday? You're not coming here, are you? Okay. I don't think. Hopefully, I'll remember to go home. So, I got another class I teach at another school, so I still got to work Monday. But thank you all.